All right, so for section 1.3b, the last time in 1.3a we evaluated some limits, but not a lot of them, and nothing that was too tricky. It was pretty straightforward. So in this lesson, we're going to kind of just focus on still evaluating limits, but of different types, okay? Limits of different types. So let's start off with this one, which a lot of times people will struggle a little bit with, just because they don't remember how to factor a cubic. So we'll talk about that. Okay, but we're going to show that f of x, which is equal to x cubed plus 1 over x plus 1, and g of x, which is x squared minus x plus 1, have the same values for all x other than at x equal to negative 1. Okay, so that and that have the same value for all x other than at x equal to negative 1. Let's give you a little bit of time just to write that down. So this one is not a limit, okay, so much as it is just a proof. Okay, show that these basically have the same values for all x's. They say except for x equal to negative 1. The reason why they say except for x equal to negative 1 is because if you plug in a negative 1 into f of x, then it becomes an undefined function, right? So we got to make sure that it can be defined, okay? So we know that x equal to negative 1 does not work for f of x. But does every other number work? Well, the way you show that two functions have the same values for all x is to prove that they're the same, right? So let's start with f of x. So we have f of x equal to x cubed plus 1 over x plus 1. Now, they're assuming that you remember how to factor a cubic, okay? If you don't remember, a cubed plus b cubed is a plus b times a squared plus ab plus b squared. I'm sorry, what am I saying? It's minus. Should be minus. It's a plus, so it should be plus minus plus. Oh, no, it did not. Hold on. Gotta stop this. All right, so like I was saying, there should be a minus here. Okay, so a squared minus ab plus b squared. There's also the other one that's a cubed minus b cubed, which is equal to a minus b, a squared plus ab plus b squared. Okay, so that would be the other one. So anyway, we factor this. This will become x plus 1 times x squared minus x plus 1 divided by x plus 1. Now that'll allow you to cancel. So all you have left is x squared minus x plus 1, which is g of x. So what we just finished doing right here, and this technique of cancellation is important for limits, but this is not a limit problem. But this technique has basically showed you that two functions are identical, right? But then they said, as long as x does not equal to 1. All right, so this is true. I've just shown you that f of x is g of x as long as x is not equal to 1. Okay? So I just finished proving what they wanted me to prove. I had to show that f of x and g of x have the same value for all x's. I just did that with the exception of x equal to -1. So x cannot be -1. Okay? So we could find the limit of f of x. So let's do that right now. Or let me not write the. Find the limit as x goes to -1 of x cubed plus 1 over x plus 1. Now notice that's just f of x from up on top, right? And we learned that f of x up on top basically became g of x, right? So remember, g of x was this function right here. So the limit as x approaches -1 of x cubed plus 1 over x plus 1 is equal to the limit as x approaches -1 of x squared minus x plus 1. Because remember, that's what we proved, right? Up here, we proved that x cubed plus 1 over x plus 1 just became x squared minus x plus 1. Okay? Now I can do direct substitution. So if I just plug in a -1, I'll get a -1 squared minus a -1 plus a 1. So this will be 1 plus 1 plus 1. So your limit is 3. So like I told you guys before, we didn't do a limit for example 1, but we kind of did the work behind what we were supposed to do for example 2. We kind of just did it early just to show you this is how you go through and break problems down. You may have to factor, right? So that was a factoring problem with cubics. Okay? So in those cases, like things like that, you may have to factor. Sometimes you may not. So let me give you a problem to try on your own. I'll give you a little bit of time to work on it. So try doing this one. Example number 3. And we're going to find the limit as x approaches 2. And on top, we're going to have x minus 2, x squared minus 4 on the bottom. So go ahead and do that. Let me move this up. And I'll give you a couple of minutes just to try it, maybe a minute or so. Try it out. All right, did anybody get an answer for it? Uh-huh. 1/4. Yeah, you can get a quarter, right? So you're going to get a limit as x goes to 2 of x minus 2, and over here on the bottom will be x minus 2 times x plus 2. You have cancellation there, so this becomes the limit as x goes to 2 of 1 over x plus 2. Now use direct substitution, so you get 1 over 2 plus 2, which is 1/4. Okay, now you can go ahead and have Desmos graph it for you so you can see and you can follow along. Okay, just to kind of see exactly what you're getting, but yeah, you'll be able to see that you'll get a 1/4 as an answer. Okay, a 0.25. Now, a technique that's a little bit more on the confusing side for a lot of people is rationalization. Okay, so rationalization is where you have to use like square roots, cubed roots, things like that. So let me show you an example like this. So we're going to find the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. After that, we just got to do the squeeze theorem and one trig property, one theorem, and then we're done after that. So 2 theorems, squeeze theorem and a trig theorem. So if you try plugging in a 0, you'll notice you get 0 over 0 as your result, right? When you plug it straight in. So that's not good. 0 over 0 is not good. So we're going to have to try to rationalize this thing. Now, normally we're used to rationalizing denominators, but you can rationalize numerators. Okay, that is possible. So limit as x goes to 0 of the square root of x plus 1 minus 1 over x. I'm going to multiply this by the conjugate of the numerator. Remember, conjugate means the same thing, just the middle sign is opposite, right? So if it's a minus, we put plus. If it's a plus, we put minus. Now I'm going to go ahead and multiply, okay? So I'm just going to FOIL. That's what a lot of people like to call it, right? First, outer, inner, last. So square root of x plus 1 times the square root of x plus 1 is just x plus 1. All right, this is what I'm doing right now. Here to here. And then the next one, square root of x plus 1 times 1 is positive square root of x plus 1. And then we'll do negative 1 times the square root of x plus 1, and then negative 1 times 1. So this will be negative square root of x plus 1 minus 1 divided by, and the bottom, I'm not going to distribute it. I'm just going to leave it like glued together. Okay, I'm just going to get the x times this. That's a plus 1. I'm just going to leave it like that. And right now you'll see why. So notice how the inner and the outer term, square root of x plus 1, they're going to cancel out, right? These are gone. So limit as x approaches 0 of x plus 1 minus 1 over x times square root of x plus 1 plus 1. Well, positive 1 minus 1 cancels. And what happens to those x's in the very front? Right here. Those are going to reduce, right? All I'm going to have left is a 1 on top. That's what's left over. That's why I don't distribute, because or else it wouldn't be so obvious to see that. Okay? To see the cancellation. It would be a little harder because you'd have more x's on the bottom. So I leave it just kind of stuck together. At this point, I use direct substitution. So 1 over the square root of 0 plus 1 plus 1. Well, that's equal to 1 plus 1, that's 2. So this is a half. So that's called the rationalization technique. Any questions on that one? So remember, you don't have to always get rid of square roots just in the denominator. Sometimes you could do the numerator, okay, and it'll work. So it's up to you how you'd like to do it, but rationalization does help, especially when you see square roots all over the place. So definitely helpful to rationalize. All right, so let me give you two special trig limits, okay? This is a theorem, but I usually don't need to title them theorems. These are things that you need to memorize. So if you have to, like, highlight these or whatever you want to do, make sure that you note that these must be memorized. So here we go. There's two of them. The limit as x approaches 0, now the easier one I'm going to write first, sine of x over x is equal to 1. Now, it doesn't just have to be x. It could be sine of 2x over 2x, sine of 3t over 3t, sine of theta over theta, as long as the angle and the denominator match. Okay? So it could be sine of 12x over 12x. Okay? As long as you get that, then it equals to 1. Now, you can manipulate stuff for it. Okay? For example, if you had this, this is not equal to 1. Okay, this is not equal to 1. This is actually equal to 3. But let me explain how. The pattern I need is I need the angle and the denominator to match, correct? How do I make the denominator match the angle? What's missing? Say again? Not the sign, no. I just need the angle and the denominator to be the same. What's missing? You guys don't know what I'm talking about? This part right here. A 3, right? But I can't just like multiply the bottom by 3, right? What else do I have to multiply? The top. So I got to multiply by 3 over 3, correct? So I'll multiply 3 over 3. So this problem will look like this. You follow? What's this equal to? That's a 1. So that means that this is 3 times 1, which is just 3. Okay? Make the angle and the denominator match. Okay? So sine of x over x is true, but it's actually sine of any angle as long as it's divided by that same number or that same term. Now the second one you have to know, kind of similar, not too close, but kind of similar. 1 minus cosine of x over x, that's equal to 0. Same thing though, as long as the denominator and the angle match, then you can put 0. Okay, so that's two special trig limits that you guys just have to know by memory in case you happen to see them. You know, like, oh, okay, notice they are both going to 0. Okay, very important. You guys note they're going to 0. And they're basically fractions. It's always over x, but one is sine of x, one is 1 minus cosine of x. Okay, so two special trig limits. Now, the squeeze theorem. This is the last thing we got to talk about. What time is it? 1:51. We get out of here at 2:07, right? I think. So let me write this out. If, and give me a second. All right, so sorry about that. Just a phone call here. So if h of x is less than or equal to f of x is less than or equal to g of x for all x in an open interval containing C and if the limit as x goes to C of h of x is equal to L, which is equal to the limit as x goes to C of g of x, then, and I'll try to draw this out for you guys, okay, and write it in a different form, but I'm just giving you the actual theorem. Then the limit as x approaches C of f of x must also equal to L. So go ahead and write that down. I'm going to kind of draw a picture here for you guys. This kind of looks like the monster from Stranger Things, right? So let's see, g of x would be the biggest one, so it's g of x, f of x would be in the middle, and h of x would be at the very bottom. So this is called the squeeze theorem because what they're saying is that the outer functions bully the middle function into being something specific. Okay? So let me kind of write it out for you guys. Not the way they wrote it there, but we'll kind of use some of their notation. But they're basically saying this. If the top function is going to converge to that point, and the bottom function is going to converge to that point, then this little function here has no choice but to converge to that same point. Does that make sense? Okay? That's what they're trying to say. So that's what they're saying graphically. Now let me do it a little bit more algebraically. So they said h of x is less than or equal to f of x less than or equal to g of x. Okay? And they said that the limit as x goes to C of h of x equals L equals limit as x goes to C of g of x. So how am I going to use this? Well, let's say I take this information here and I do the following with it. So I know h of x is less than or equal to f of x is less than or equal to g of x. So why don't I give all of them a limit as x approaches C? So limit as x approaches C of h of x would be less than or equal to limit as x approaches C of f of x, which would be less than or equal to limit as x approaches C of g of x. I mean, that's perfectly legal, right? Like you can multiply all the functions by 3. You can divide all the functions by 12. You can apply anything. You can apply a sign to everything inside of that inequality. As long as you apply it to everything, right? To keep it mathematically sound. So that's all I did. I just said, I'm going to apply a limit as x approaches C to everything. Well, what's the limit as x approaches C of h of x? I think I wrote it right here. This is L, right? Less than or equal to the limit as x goes to c of f of x, less than or equal to what? L. So if the limit as x approaches c of f of x has to be bigger than L or equal to it, or less than L or equal to it, then what's its only option? Yeah, so the only option for f of x is to take an L, right? So the limit as x goes to c of f of x must be equal to L. It got squeezed. It has no choice, right? It got bullied into being a specific function, a specific value, not a function. So yeah, so that's what this big old theorem is basically trying to say. They're saying, look, we got three functions. There's a small one, a big one, a middle one. The big one and the small one kind of meet up in the same place. So the middle one has to at some point, because it's in between. So if the bigger one and the smaller one meet up at the same place at a specific point, then the middle one must also meet at that same exact point, because it's getting squeezed. Has no other choice. Okay? So that's the squeeze theorem. So I'll stop there, and let me give you guys your homework for this section. Let me see.